Has anybody noticed if the comments are recorded in the recording? Oh, good. If you're not using Windows, create a virtual machine. That's not ideal, but surely it is available. Oh, I see. They're not working properly. Okay. So I've been giving you a little bit of time to get it working. You should get to a screen that looks like this. And that looks like this. Let's remember to put my cursor on the actual application. And essentially, we're going to do create new with a wizard. That's the click. That's the first click we're going to do. So hopefully you can easily get two windows onto your screen. The one is your own. One is your own DWSim running, and this one is the Blackboard Collaborate thing. So create new. I'm going to click that now. Right, welcome to the simulation configuration wizard. Next to continue. And so I guess it's a good. Hello.
Sorry to interrupt, Prof. I just want to let you know it seems like it's not showing the pop-up window, but it shows the DWSim application. So maybe the best thing to do is to share your extra screen, and then it'll show everything that pops up there.
That's a good idea. Right, so I'll put this on.
Just so they can see the pop-up window, but I'm sure they all see it, those that are going along.
Yeah. All right, I'm going to cancel this so that I don't have a pop-up screen, then I can maximize. And then I'm going to go back to share content. And we stop sharing this content. We share screen, and it's going to be screen 2. Thanks, William. That was useful. Okay, now we've got to get the wizard going again. Is it a tool? Let's have a look. File. New process simulation model. Yep, that looks like it. Simulation configuration wizard.
Great, we can see that, Prof. Thank you.
Okay, great. Okay, next. And so the first thing we're going to do is to choose our compounds. And if you read the announcement, or the what do we call it? Today we're going to try and simulate a water ethanol simple gas liquid separation. So it's just a tank. You have a pipe going into a tank. It operates at a certain temperature, and therefore you'll get a certain amount of liquid coming out, and you'll get a certain amount of gas coming out. And they will have different compositions because because we have different vapor pressures for the two. So search, we look for ethanol. And there we have it. We check that it's the right thing, and we add it. Now, don't go on to next now, because you must choose all of your compounds before you go on to next. So you just type in your next one, choose it. Choose it. Oh, and then if we delete here, there we go. We see that we have chosen. The ones you've chosen will be at the top of the list. And that's all we need. These are the correct formulas, so happy with that. Okay, I'll give you guys time if you want to follow up with that. So it's only when you've got all of the compounds that you really want in your simulation that you would go to your next. Okay, here we go. So what we've been doing down here is following. We've done compounds. Now we're doing the property packages. I'm going to look for 2 property packages. I'm going to look for Unifac because we do need a package with ethanol and water. These are highly interactive, and we know they form an azeotrope. So we will be looking for a thermo method that does that accounts for interaction between molecules. So Unifac does that, and we add it. Now this is important. It has to appear in this list here, so we have to add it. And now we're going to go and look for another one. And the other one that we use, and this is a very useful one, Peng-Robinson. It's an equation of state simulation model, a property package. So it is very good at going to very high pressures and temperatures, and it's a much more general purpose. You'll find that many more models will work on Peng-Robinson than they will on Unifac. Okay, so we choose Peng-Robinson and we add that. Right, now we've got all the packages we want for this particular simulation. And now we can go to next. All right, so thankfully, the default system of units is SI. Now, we are not going to be using SI, and I don't want you to use SI in design project either. SI is fine for journal articles and things like that, but if you work at Sasol, and many students used to go and work at Sasol, they're not hiring anymore, I guess. They will insist that you use degree C, and you use, so there the temperature, you'd choose degree C, and pressure you'd use kPa, not pascals. Pascals, I mean, atmospheric pressure is 100,000 pascals, so that's not a useful thing. So we want kilopascals, and C5 tends to give degree C and kilopascals. So let's choose that one, and there you can see temperature is in degree C, pressure is in bar. Okay, bar is fine. You can clone it, and you can create your own set of units, and there you'd be able to choose. This is also more useful because it's kilograms per hour instead of kilograms per second. So that's what we'll choose, right? C5 and finish. Right, blank screen. Then you have to wonder what you're going to do. Okay, let's have a look at what we've got here. We've got spreadsheet, dynamics, utilities, optimization, results, plugin, Windows, View, help. We've got a lot of icons. There's an important one, solve spreadsheet, flow sheet, board solver. There you can go to dynamic simulation, and you've got printing. Okay, but now, more importantly, down at the bottom, here are unit operations. There you can put in streams, you can put in different unit operations down here. So the one we're looking for, a gas liquid tank, essentially, is going to be this one over here. So let's choose that tab, and gas liquid separator is pretty much what we want. And you just drag it and put it into your window. Okay, and now you'll see every time you do something, it reflects in this screen at the bottom. It gets reflected all the things that you have done. So now we're going to click on this one to get its properties on the screen. If you just click, you left click, normal click, you'll see this is called separator number 1, SEP 1. Status is not calculated because we haven't told the simulator anything to do with this particular thing. So what we need to do is to add in streams. You'll have a single stream coming in and you'll have 2 streams coming out. And for every unit operation, there'll also be an energy thing, because a unit operation typically has a duty, and you need to either add energy or subtract energy or lose energy if it's not properly lagged, insulated. So let's put in connections. Inlet stream 1. Now this is really important. That little green thing. Oh, it's in French. Green, yellow. That yellow thing is when you want to create an inlet stream for the separator. So we click on that one, and look at that. There's a stream 1, and it's being created. Now we need to put in our gas and liquid streams, and here we go down to the bottom. There's a vapor stream, and there's a light liquid stream, heavy liquid stream. That's if you have 2 phases. So let's just add the vapor stream, and we add the liquid stream. All right, let's just keep an eye on the chat. I just want to see if people are getting lost. Okay, good. So far so good. Hope everybody is with me. Yeah, Philip.
Does it make a difference whether we choose the light or heavy liquid stream if we only have 1 liquid stream coming out?
I am not sure. I haven't tried that yet. Maybe William or Hilton can tell us. By the way, I haven't introduced you. You'll see that the moderators on the list are William Bosch and Hilton Trollope. No, that's not Hilton. I used to know Hilton when I went to university. Brendan Trollope. And they were 4th years last year, where we had to quickly learn this DWSim. And they did their entire design project using DWSim. So I've roped them in because I'm doing DWSim for the first time now, and they've been helping me understand what to do. So they gave me this wonderful tip about using these little yellow arrows here. So William, you've never tried putting in a heavy liquid stream instead of a light liquid stream?
I haven't tried it, just unless I was using liquid equilibrium. But what I'm going to do now is I'm going to fiddle bits, and then I'll come back to you, and I'll see if it makes a difference.
Okay, yeah, that's fine. Thanks. All right, so we haven't done an energy stream. This thing is not going to run unless we put in an energy stream. Put that one in. And there we have it. Okay, so we're going to now choose to override the separation temperature, because there's going to be no separation at 25 degrees C. And we still need to choose a, all right, I'll change this one to, let's say, 90 degrees C, and enter. Script data updated successfully. And now we need to actually choose what this stream is. At the moment, it's got, just hovering over it without clicking or anything, it actually shows some information about that stream. It's automatically chosen that there's going to be 1 mole per hour. and that is the equivalent of, sorry, 1 kilogram per second, a kilogram per second. So if you look down, I can't show it now, but if you look down on at the bottom box, it says 3,600 kilograms per hour. And the mole fraction of vapor is 0, which is understandable, especially if you've got half ethanol, half water at 25 degrees C. Okay, so now we're going to start changing this thing. So I'm going to click it. As soon as we click this, we'll see the left-hand side, which used to be SEP01, is going to change to the stream. This is M stream number 1, and this is what we've got in it. Now, important here is to note these tabs over here. Okay, so the compound amounts, we're going to change to be ethanol 0.1, as I said in the announcement, 0.1, and the water we're going to have as 0.9. And these are mole fractions. Now you can choose whatever you like over here instead of mole fractions. But in this case, we're going to use the mole fractions. If we look at mass flows, that's quite different because it now depends on molecular weight. Whoa, that's wrong because that's 2,500. Oh yes, 2,000. No, 2,000, and this is 1,000. Let me just go back. Oh, I know what it is. I was using 90% instead of 0.9.
You just must accept your changes.
Sorry?
Remember to just accept your changes, otherwise it ignores whatever you just told it.
Ah, okay. So now we go 0.1, 0.9, and accept changes this time. Yes. Right, now we can have a look. What have we got for mole flows? That, if we look at mass flows, got that, and the total of, if we add those together, we get that 3,600 kilograms per hour that we were talking about. So essentially, this stream now has been completed as far as I can see. Stream conditions, 600 molar flow. And because we added mole fractions, we could change the mass flow now to whatever we wanted. But let's leave it at that. And now let's see, we can solve, this thing is solved. It ran for the stream, and the flow sheet was also calculated successfully. So I suppose this thing is solved. Am I right, William? Let's just solve flow sheet anyway.
So Prof, there's that little on button next to the solve flow sheet. Do you see that little on button with the arrow up at the top where it says solve flow sheet? That thing, it means that it calculates it whenever you make a change. It automatically calculates it. So because you have that on, no, just the on button. Just the on button.
Oh, that one. If it's on, it automatically calculates.
Yeah, it automatically calculates.
Okay, wonderful.
Yeah.
All right. So it was calculated.
That, it's already solved it.
Yeah. Okay, so now let's have a look what's happening here. Let's have a look at the energy stream. There we go, 683 kilowatts. And that is, it's a positive number, so it is required. It's endothermic. We need to put in 683. Now let's have a look at this liquid stream. It's a little bit there we go. Okay, if we move it a bit up, we look at the gas stream here, and we can see it is vapor only, and it is 888 kilograms per hour. And there should be, and pressure. Ooh, no, I didn't want to do that. I wanted to, oh yeah, there we go. I must not have my pointer pointed at it. And then let's look at its composition. Ethanol, it's about 1/3 ethanol and 2/3 water on a molar basis. So there you can see, oops, I mustn't move my cursor. And now it's disappeared. Now where do I get that liquid, that vapor composition from? There we go. So right at the top there, compound amounts basis is molar fraction, and we've got 1/3. Remember, we started at 10% molar ethanol, and so it's been increased to 33% molar ethanol. And similarly, we can go down here and look at that. We've got 95% water and only 5% ethanol in the bottom stream. So we successfully managed to separate most of the ethanol off in the single stage. Yeah, it seems like you've got to move the screen to see those results. You've got to move this thing in the screen. You've got to move your, you just by clicking and dragging elsewhere, you can see the rest. But there should be a result somewhere else that you can, if you click on that stream, you should see the results over here. So you can see compound amounts and stream conditions. All of that is at the side here. And you can look at results. Phase properties, compounds, phase properties. Yeah. So the whole thing is solved, and you'd be able to look at anything you require out of these things. Right. So I want you to look at this composition over here. Set point temperature override isn't accepting. Yeah.
It's like I was just running my simulation. It seems like the simulation doesn't even want to compile. It shows that my vapor stream's got like 0 mass flow, 0 molar flow, almost everything. Enter after entering 90. Let me check that quickly. Thanks, Angela. I'll try.
Who was that, Gareth? Ah. Okay, I'll give you a little bit of time to make
All
sure
golden
you get
now.
running. If you have one, gee, let me get to. Wow, there are lots of comments. I've been missing them.
So, Prof,
wait.
I want to show them as well. If you go to the feed stream to this flash drum, and you go look at the phase properties under the result. So if we just select mass stream 1,
if I go to results and I go to
phase properties, but of mass stream 1. So the
yes.
feed, yeah?
Yes.
And then we go
and
results, and then we go to phase properties. Just above there, Prof. There we go. Do you see that it says mixture overall liquid 1? Because this mixture mixes together, like it's not two separate liquids that are immiscible, it'll say liquid 1, and then that's the reason why we only need the light liquid and not the heavy liquid. So
okay,
that liquid 1 should be the same
went
as
into
overall
two
liquid.
phases. If it was two phases, it would show 2 tabs here.
Exactly. So if we were to change the temperature of the stream to like 90 or something, it'll probably show liquid and vapor, liquid 1, vapor 1. But because it's at standard temperature and pressure, it's at a liquid because it's ethanol and water. It's miscible.
Okay, yeah. If we had a vapor mixture here, let's change its. No, I don't want to change its temperature. I want to change the. I want to change the thermo method because I wanted to show you that we've got 95% water here, And if we change the thermo method, I got to figure out where to do that. William?
Okay, so Prof, click on the separation unit, the flash drum.
Oh yes, it's linked to the
And then
actual
it's-
unit operation, and there, property package.
100%.
Right.
Because we want the calculation, not how the streams are.
Yes. And we don't have to accept now, eh?
Yeah, it's already run.
Just run.
Yeah,
And now we're
because it's
going
on
to
the
look
auto
at this.
run.
03, look at that. There we go. You can see how much that has changed the composition of stream number 3. So now we've got 0.2% ethanol, whereas previously we had something like 5% ethanol. And that is because this is the wrong answer. It's a nicer answer because we've got rid of more ethanol, but it's the wrong answer because Peng-Robinson is an equation of state method, and the equation of state method does not model the interactions between molecules very well. The polar molecules like water and ethanol. Okay, now let's go and have a look at this stream 1, and we're going to change its temperature. Oh, right. Let me go back there and change back to Unifac. Okay. And now we go to stream 1 and we change its temperature to 90 degrees. Or let's change it to 89 degrees. Mixture, input data. There we go. So we assume this is going in at 89 degrees. And that should automatically run. And therefore, if we go to results, overall liquid, liquid 1, overall liquid molar fraction. I'm looking for fraction that is vapor phase.
So, Prof, you're in the results of the stream train in. If you want to look at the results, you have to go to either the vapor stream or the liquid stream on the other side. That's only.
Yeah, no, I want to see that because if we make the stream, no, it hasn't changed. I haven't said accept. 89, it is 89, but I must accept this, or I must remember it.
You must just
as soon as I make it
on the 89.
it should be a vapor liquid stream.
Yeah, so just click that 89. Click that 89 and then press enter. That seems to be okay. Let's see if we go back now to results. There we go. So now it's mixture, vapor, overall liquid, liquid 1.
Oh, right. Vapor. Okay, we've got a vapor stream and a liquid stream. And we've got an overall liquid, which is probably going to be the same as liquid 1, unless we had 2 liquid phases. Okay, I understand. So now let's have a look, because we're putting in this at 89 degrees C instead of 25. Let's have a look at the energy. It used to be 880 or something like that, or 600 and something, but now it's gone down to 87 because we don't have to heat it up so much to get up to 90 degrees C. And this should give the same results here, mass flow of 888, and this one, yeah, we're back at the 95% water and 5% ethanol because we've gone back to the Unifac turbo method. All right, so that's pretty much what I wanted to cover today. So let's have a look. Is everybody there? Is everybody with us? Thanks, Gareth. Good.
Prof.
Yeah.
So I just want you to go to Insert tab up there. Insert.
Over
Insert
here
at the
somewhere.
top left next to File. At the top. And I just want you to put in a table, a property table that says everything about the flow sheet.
There.
So insert,
Menu item.
yeah,
Good.
and then master property table. Okay, then go back to the flow sheet and you can click there. That's where it is. You can now click it, double click it. And now you can choose the streams you want to demonstrate.
What we put there.
Yeah.
That's neat. Temperature, pressure, mass flow. And where does it say? I want the different components.
Components.
Oh well, let's just leave it at that. And where's okay? Configure name.
Just select those objects when you're finished there. So you can click on the left-hand side of that small box, select all objects, or you could do that, yeah.
Oh, I
and
see,
then when you
right.
press escape now, it'll just generate it and pop all the information in there for you.
Oof, escape sounds like it's going to
Sorry.
lose everything. It's not escape.
No, just the little X button on the little
not that one.
Box. That one, yeah, that one. Go ahead.
Oh yeah, look there.
There you go.
Oh. Yeah, you live and you learn, huh? That's rather useful. Because now let me try and change something here. Mixture, input data, compound amounts. 0.8, enter. Accept changes. I'm learning. All right, there we've seen all these numbers now change. Good. Okay, cool. Thanks, William. That's a useful little thing to know. So can you impart more wisdom to us, please?
I can try, Prof.
Yeah, you have to explain because I've got the mouse.
Yeah. I just want to show them. So these are the normal separators that they give you, okay? But combine multiple processes from reactor into distillation column. Okay, Chandra, so I think we'll do that next time because this is just an introduction. But I'm going to show you where all the things are. So in each of these tabs, you've got different equipment. And then columns, these are your distillation columns. So there's a shortcut column, absorption, distillation, and a chem sep. Okay, so the shortcut column is very similar to what we would do in Aspen. So we just do the shortcut method, and then it'll just be fug. But then you can do rigorous column design using the other guys. And that's pretty much the only thing I'll say for now. Because I don't think we haven't prepared.
Columns, you need to get conditions that work, that are viable. Because if you start with a ChemSep column, you might be putting in conditions that are simply not viable for a distillation column. So with a shortcut column, you can get at least something that's going to work, and you can start. That's your starting point to get a ChemSep column to work. Okay. Oh, it does do solids. That's cool. Okay, reactors. Now, in design project, you are almost certainly just going to use conversion reactors, because when you do your literature about this process that you're designing in your design project in CPJ, you're gonna learn that it is difficult to get anything more than, say, 70% conversion. And so you choose a conversion that is reasonable based on the literature, and then in your reactor design, you will go and model that in usually another language rather than doing it in DWSim. So you'll know that your aim is to get 70% conversion, and then you will use your Python or whatever your preferred tool is for designing the reactor itself. So this is the one that you're going to use, and CSTR is nice to use every now and then. Equilibrium reactor is nice to use because, well, this one gives an approach to equilibrium, I imagine, if it's much like Aspen, and the Gibbs reactor is a full equilibrium reactor. So it will distribute to all of the compounds that you've got in your data that you've selected as part of your simulation. And so you put in various compounds in the incoming stream, and it will distribute them according to thermodynamic equilibrium to whatever compounds you do have in your simulation. And that's the Gibbs reactor. It is a useful thing to see if it is thermodynamically possible to get a certain conversion. If it's not thermodynamically possible given a certain feed, that's what you'd learn from your Gibbs reactor. You also will see what temperatures are favorable. For instance, it may be that you need to operate at a temperature below a certain threshold to get a certain conversion. So a Gibbs reactor is useful to have. And then plug flow reactor, there you got to put in the kinetics, and usually kinetics for a catalytic reaction, which is what you normally have, they are fairly unique. You're not going to have that model in this reactor. So it is not that often used, but I do believe it's easier in DWSim to put in your own unit operations than it is in Aspen. So you may be able to put in whatever kinetic model you'd like in this thing. But I want to suggest, don't go for these kinetic model reactors. You go for one of these other reactors. So even a continuous stirred tank will probably have kinetics in it. You just go for a conversion reactor for the most part. Almost all simulations I've done throughout my career have been using conversion reactors. It's much better to do the detailed modeling in a programming language of your choice. Right, that's reactors. Columns we've looked at. Solids we've looked at. Exchanges. A heat exchanger. What's the difference between a heater and a heater cooler and a heat exchanger? The heat exchanger, you've got to actually show what is your utility that you're using. Are you using cooling water? Are you using steam? Whatever, you've got to show that on the thing, and it must be a stream. In other words, there must be a flow. If you use a heater or a cooler, let's say it's a cooler, and you're using cooling water as your utility, you don't have to have the cooling water coming in at a certain mass flow rate and going out at another mass flow rate and temperature. You can just say, I'm removing so many kilowatts of energy, and then the stream, the process stream, will cool down. So again, these heaters and coolers are very useful, and you will seldom actually use the heat exchanger in your simulations. Mixer splitters. This is something that I'm not too sure how DWSim handles mixing. With Aspen, you can put in multiple streams into the same. In fact, this we know you can put in multiple streams. You can put in multiple inlet streams into the simulation. So that's okay. So you don't often need a mixer as such. But a stream splitter you often do need, and especially when you're doing purges. Right, and then separators and tanks we've looked at, and pressure changes. So they're orifice blade. Compressor. So recognizing that a compressor is different from a pump, because a compressor you use for vapors, a pump you use for liquids. Expander is also usually used for vapors, and that's why it's called an expander. As pressure decreases, the volume flow rate gets higher. So that's why a compressor is written in this direction. The volume flow rate will decrease as you go from the one end of the compressor to the other end of the compressor. In an expander, the opposite happens. And a valve when you need to decrease pressure.
Prof, can I?
I'm just reading comments. Yeah.
Do you know if I share screen? I just want to show them how they can make it solve faster as well, and also remove the auto solving, I think.
What about share screen?
I just want to show them because it's deep in the settings. I can explain it to you if you would like.
I see. I can share the screen with you.
Because when you get to, say, 5 process operations, it can get quite time intensive or CPU intensive.
I think let's call it a day. We're getting towards the end
we'll
of the
do that
lecture.
next time.
Yeah, let's do something like that next time. Okay,
Fantastic.
thanks guys. Let's stop the recording, and I will make sure that I post this, whether it's on YouTube or in ClickUp. I will post this as an MP3 so that anybody who got lost somewhere during the process can catch up. Oh, that's stopping that. Let me see. Stop recording.